In Chapter 10 of your statics textbook, it focuses on the area moment of inertia, which is a property of an area. You might say, what's important about the area moment of inertia? A good illustration of that is a yardstick. And so if you take a yardstick on its flat edge and put a load on it, it bends easily. If you turn it on its end and put a load on it, it bends much less easily. And so this is basically like a beam or like a joist in your floor or your home. Most builders know to stand a board on its end, and it's stiffer, it's more resistant to bending. On the other hand, if you take that board and lay it on its side, it's much less resistant to bending. Why is that? It's the same cross-sectional area. The reason for that is called the area moment of inertia, and it's a property of this area. And so the area moment of inertia of this area about this axis, where the area is farther away from the axis, is a larger number. Whereas if you turn it this way, the area moment of inertia about this axis is quite a bit smaller because the area is so close to the axis. So one of the things that engineers do is when they design, when they use materials, we want to use materials in their most efficient way. And so most of you have seen like I-beams that have a relatively large flange at the top and the bottom and a relatively narrow flange in the middle. The reason for that is that's an efficient use of that material. And so when you put that beam in bending on, when you stand that beam up vertically and put a vertical load on it, the top flange and the bottom flange carries a significant amount of the bending stress and the load and makes that beam very stiff. And so it's an efficient use of material. So that same material just collapsed without the flanges, collapsed into a vertical beam, or even worse yet, turned onto its side, is much less resistant to bending. So the area moment of inertia is a number that it indicates the property of that shape and the degree to which that shape resists bending or resists bending stress. A number you'll also see in this chapter briefly is called the polar moment of inertia. And the polar moment of inertia is a property of a shaft to resist torque. And so a torque, a shaft resisting torque, it's a function of the part of the shaft that resists most of the torque is the outer edge of the shaft. And so an efficient use of material in a drive shaft, for example, is to make it hollow. And so by making a drive shaft hollow, you probably see it in some large trucks. The large drive shaft is quite large that goes from the back of the transmission to the rear axle of the truck. And it's fairly large. Well, that large drive shaft is actually hollow. And so it's the outer wall of that drive shaft that carries most of the torque. And so you can actually make a lighter drive shaft that carries sufficient torque by making it hollow and makes it more efficient use of material. So ultimately, that's a big part of what engineers do. We try to use less material to achieve certain strength design targets that we're looking for. That's one reason why we're interested in trusses, because trusses are relatively lightweight, but they carry relatively large loads. But this chapter, area moments of inertia, properties of areas, is a key number that we're looking for. Here shortly, I'm going to talk through a handout that talks about some of the formulas that you will learn in mechanics materials that use the area moment of inertia property. And that will help you further appreciate what that number is all about.